Okay, so our objective today is to review probability. All right, so we were going to do an experiment for the warm-up, but with COVID, along with the timing of me not being here last time, we're just going to talk through it. Okay, so the warm-up, we were going to take thumbtacks and you were going to roll them, 2 of them. Okay, and you would count how they landed. Did they land on their backs, on their back on the side, or on their sides? And the idea is, what is the most probable? What's the probability that it'll land back side, or side side? Could you guys figure out a way to figure that out mathematically? Okay, well, let's think about if you flipped a coin, okay? If I flip a coin, what's the chance of me getting ahead? 50-50. Probability of head is 1 out of 2, right? Mathematically, you could say, well, half of it's one side. You can find the area of this side, area of the back side, half heads, half tails, and you can figure that out, okay? Excluding that maybe it lands on the side, assuming it's equally weighted. You could use geometry or math to figure that out. You could also think about it as you could get a head or a tail. So as our sample space, there are 2 options, 1 out of 2, okay? You can figure that out mathematically, or you could flip a coin a bunch of times and see how many times you got ahead. But if you did it 10 times, would it be too weird to get 7 out of 10 heads? No, okay? It is a real world probability. The theoretical probability is you'd get exactly 5 out of 10, 50-50. But in the real world, you could get 7 out of 10. You could even get 1 out of 10 maybe. So if you wanted to figure out using a real world experiment, you'd have to do it over and over and over again. The more you do it, the closer it would get to 1/2. So here's what I would have had you guys do. I would have had you flip them and we'd combine your data. So here's one person's data, okay? They flipped it 25 times. They got 40 backbacks, 21 out of 50 heads or back sides, and 9 out of 30 side sides. So their probabilities based off of their experiment was a 40% chance of landing on its back, both of them, 42% back side, and 18% side side. You can see that everybody has a varying answer. Do you notice anything about these answers though? Each roll is equal to 50. Yeah, so each person's is going to add up to 50 because they were told to roll it 50 times and count what they got. That's a good observation. What else? What do you notice about the separate observations? These were the actual amounts. Like this person got 29 back sides, which was 48%. This person got 6 out of 50, which was 12%, or 10%, or 22. What do you notice about the amounts? Side sides seem to be the lowest, right? And then these seem to be slightly higher. So that variability happens when you do a real world experiment. What I did was I ended up combining all of them. So 50, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, out of 13 times 50, out of all of those rolls, I refigured them out and it turned out to be about 46% of the time you'd get back, 42.5 you'd get back side, and about 12% of the time you would get side. This is an experimental probability. The more I can do this, the more accurate these will get to be the true values. It's a long run thing, okay? So if I were to combine, if you guys were to do it, and then I would combine it with the next class and a next class and a next class, same thing with the Tootsie Pop, the more you do it, the closer you get to the real value, okay? So some things you can only figure out experimentally, such as rolling these. Because even if you found the surface area and stuff of this, you'd have to figure out the gravitation, the rotation, all of that. It'd be a pain. So some things, the only way you can figure out the probability of them happening is to experiment. And then the point is you have to do it over and over and over again to get closer and closer to the true value. And some things you can do mathematically. So here's what it's saying. We're going to talk about experimental probability. You do trials. The number of times an experiment is repeated. So in this case, for each student, the trial was 50. And then when I combined them, what was it? It was like 650 trials. Okay, something like that. Outcome, the different results possible for one trial. So in our case, it was back, back, or side, side. And notice we combined back, side, and side, back. If you were doing this mathematically, they would be two separate ones that you would have to add up. Okay? Frequency is the number of times a particular outcome is observed. So in this case, the frequency was 20 for this one. For another person, it was 22. Okay? And relative frequency is the success divided by the total, or the percent, which you already know. Okay? All right. So that's what we did here. Ideally, we would have done this as a warm-up, but it's introducing to experimental probability. Here's some more vocab. Are you guys okay if I take can I take the microphone off and you're okay, or do you need it? Raise your hand if you need it. Okay, because I think it's going to make this video weird. All right. An experiment is something with an outcome. Flipping a die, or flipping a coin, rolling a die, flipping thumbtacks, whatever it is we were going to do. Okay? The event is any particular outcome or group of outcomes. Example, one event from the rolling of the thumbtacks would have been back, back. That's an event. Getting a head is an event. Getting a tail is an event. The sample space is the set of all possible simple events. Okay? And the complement is all outcomes not in A. So we're going to talk about, it's kind of the opposite. The complement of heads is tail. The complement of back, back would be back, side, and side, side. Everything that it's not. And the notation for complement, if this was event E, the complement of it could be E line, EC, EI. You could also say not E. There's lots of ways to write it. Okay. Oh, actually, that's approximately E. Not E would be like that. Okay. So for equally likely outcomes, okay, you'd say the probability of an event happening is the number of successes divided by the total options. Right? Every time we roll those thumbtacks, it's the same probability each time. It doesn't change, like magically they change weights, and now you're more likely to be on the back. Okay? So here's some examples of sample spaces. Okay, a sample space for the thumbtacks that we were supposed to roll would have been back, back. The first one back, the second one side, or the first one side, the second one back. We do keep those separate, right? For the real world, I just said call it the same thing. But really, you keep them separate theoretically, or side, side. That is a sample space. And then these are some events. So one event might be back, back. So the complement of that event would be back, side, or side, side. Okay, if I were you, I'd be taking side notes or following along. Example for a coin flip. Okay, the sample space of a coin flip is heads and tails. One event would be a head, so the complement of that event would be a tail. And then the probability of getting event E, which is a head, well, that's a head over the two options, head over tails, 1/2 chance. So it's just showing you how to write it. These little squigglies mean all of the elements, all of the things in a set. Okay, 2 coin flips then could be head, 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 tail, tail, head, or tail, tail. So an event could be head, head. How many ways to get head, head? 1 out of 1, 2, 3, 4 options. Okay, so there's a 25% chance of getting head, head. which means what's the probability of the opposite of that? 3/4. If you have 25% chance of getting head-head, there's a 75% chance of not getting head-head. Now, one way to multiply these, you may have seen the multiplication rule before, where you'd say it's the probability of getting ahead times the probability of getting ahead. What's the chance of getting one head? 1/2. What's the chance of getting another head, assuming you already got a head? 1/2. 1/2 times 1/2 is 1/4. So if you're doing two things at once, you could multiply, but right now we're just looking at the sample space. Any questions? Okay. So I've done it for a couple of other things. I've done a 6-sided die, right? So those are my options. Maybe event is getting a 1 or a 2. So then the probability of that event would be 2 out of all 6 things, or 1/3. These would be getting 2 dice. So this is die number 1, die number 2. So you rolled a 1 and a 1, okay? And then I ask a question. My event is the probability of getting an even sum. So adding them up. Well, I'm going to highlight them. How many ways could I do that? 1 plus 1 is 2. Okay, 1 plus 2 is 3. That wouldn't work. 1 plus 3, this is 4. That's even. That's even. These are all the even ones. If I added them up, they'd be even. So there are 18 out of 36, or there's a 1/2 chance of rolling 2 die and adding them up and having it be an even number. If there's a 1/2 chance it's even, then there's also a 1/2 chance that they would add to odd. Things you also need to know, in a deck of cards, there are 52 cards, 4 suits, half of which are red, half of which are black. There are aces, 2 through 10, jacks, queens, and kings. That's 13 cards per suit. So 13 hearts, 13 diamonds, 13 spades, and 13 clubs. If you haven't memorized that, you're going to want to memorize it between now and the final. A couple of other things. A certain event has a probability of 1. Okay, what's the probability that you're going to go home today at some point? 1, 100%, I hope. Okay. An impossible event then has a probability of 0, which means everything else has to be between 0 or 1. Any probability has to be between 0 or 1. It's obviously a joke when they say it's 110% chance it's going to happen. That means, of course, it's going to happen, right? It's always 0 to 1. 0 it didn't, 1 it did. Normally, I would have you guys do these, but I want you to think about it. Theoretical probability is the measure of chance that an event occurs in any trial of an experiment. Okay, and we're going to use math to figure it out instead of doing the experiment. So, a ticket is randomly selected from a basket containing 3 green, 4 yellow, and 5 blue tickets. So I drew a picture. What's the probability of a green? 3 out of all 12, or 1/4. Make sure you show work. All right, obviously, that's 1/4, or 0.25, or 25%. But I know if they were doing the final, they'd be looking for the fraction first. So show work. Okay. And I know in a lot of cases, they'll give partial credit for the numerator and the denominator. So just by knowing that there were 12, you could have gotten half off, or half the points. Okay, what's the probability of getting a green or a yellow? 3 plus 4 is 7. Or means plus. Okay, and means multiply. What's the probability of getting an orange ticket? 0, obviously, because there aren't any. What's the probability of getting a red, a green, or a yellow, or a blue, if you have to draw one out? That's 12 out of 12, or 100%. This little U, that's a union. It means plus as well. It says this little n means number of. The number of things in A plus the number of things in not A equals the sample space. Okay, what? That means this. How many things are in my sample space? 12. There are 12 different tickets, right? Well, the number of things in green, that's 1, 2, 3, plus the number of things in not green, that's 9, equals the sample space. That's all that's saying. Okay. Also, the probability of getting a green one plus the probability of not getting a green one has to add to 1. So if I was taking notes, maybe what I'd have to write is that this is saying the probability of getting an A, of event A happening, plus the probability of event A not happening. Well, one of those two things is going to happen, so it would add up to 1. Similarly, event A is 1 minus event A didn't happen. Or no A is 1 minus A. It's just saying the whole thing adds up to 1. So if you subtract the part that you're looking at, what's left is the other part. Several different definitions for complements. Any questions? This is the worst way to learn. Yes, dear. Possibility of event A happening. And then the other one is the probability or possibility, it really is probability of event a complement happening, or that means A didn't happen. So here's some more examples of that. It says an ordinary 6-sided die is rolled once, determine the chance of getting a 6, 1 out of 6. Of not getting a 6 then would be 5 out of 6. Of a 1 or a 2 would be 2 out of 6. A 1, this is 1, this is not a 1 or a 2, well then that would be 4 out of 6. You really need to spend some time working on these because you'll have questions. Okay, 2 events are independent if the probability of one occurring is the same whether or not the other events occur. Are the following events independent? A fair coin is tossed 2 times. The events are the first coin tosses a tail and the second tosses a tail. Does knowing you got a tail the first time change your probability for the second time? No, so it's independent. A coin is tossed and a die is rolled. What you get on the coin does not affect the die or vice versa. If you're falling asleep, go get a drink. Using a standard deck of cards, you draw 2 cards without replacing them. Probability you draw a king and then you draw another king. Well, first chance of drawing a king is 4 out of 52. But if you grabbed a king, your next chance is going to be 3 out of 51. Knowing you got a king the first time changed the probability the second time, so they were dependent. So we have combining probabilities. Okay, this and this mean and, okay? Probability of A and B, that's that little U. It says the probability of A and B for independent events. If A and B are independent events, then the chance of both things occurring is just multiplying them together. Okay, so suppose we flip a coin and roll a die. The sample space for a coin is heads and tails. The sample space for a die is 1 through 6. So these are my sample spaces. And I want the event of getting a head and getting an even. That's the same thing as the probability of getting a head times the probability of getting an even. So you just find the two separately. If you want them both to happen, you multiply it together. So how many heads? 1 out of 2 times, if I want an even, that's 50% chance, times 3 out of 6, or a 3/12 probability, or a 1/4. 25% chance I would get a head and an even number. Okay, this is a head and a 5. A head and a 5. 1/2 chance I got a head times, that's the probability of a head, times the probability of getting a 5, which is 1/6, or 1/12. Okay. I think I want to take a sidetrack just right there and point something out. Again, the difference between independent and non-independent. Okay, is it frozen? What's it doing? Okay, here we go. There we go. So let's say I usually keep normal years a stick of students' names, okay? And maybe in that I have 30 sticks, 10 are for boys and 20 are for females. What's the probability of me getting a female stick? Anybody or everybody? Are you guys good with 20 out of 30? Okay. Probability of getting a female and a female with replacement. So I draw a female stick. Okay. I used to have sticks. Pretend these are sticks. I draw a stick, it's a girl. The chance of that was 20 times 30. Now what's the chance of me getting a girl again? 20 over 30. So the chance of getting a girl and a girl is whatever 20 squared times 30 squared is, right? That is independent. What I did on the first time did not affect the second time. However, if I did it without replacement, the first one's 20 out of 30, but now I'm holding the girl's stick. So what's the chance of me getting another girl? Okay, this one depended on this one. And that's the difference. If they're independent, okay, I'm going to say this is girl 1 and girl 2. The probability of getting a girl 1 and girl 2 when they're independent is just the probability of getting one girl times the probability of getting another girl. That means they're independent. You don't have to account for anything changed. For this one, the probability of getting a girl and another girl, that's the probability of getting a girl times the probability of getting a second girl given you got a girl the first time. So you still multiply when it's and, but this one is going to change a little bit. How do you guys feel about that? Let me see your thumbs. Okay, I don't even know if we ask you to use this formula yet, but it's the right place to have this discussion. So right now, all you need to know is that and means multiply, and we're dealing with independence, so you don't have to change the second one yet. Okay. So here we are, okay? Now we could also combine them with and, or not and, with plus or. And it's the probability of A or B, which is the probability of the same thing of A union B, okay? And really, this is the formula. You have to think about overlap. This is the or formula. Or means and, but you might have to subtract out the overlap. So here is a Venn diagram of all the cards in a deck, okay? The red cards and the black cards. Oh, red cards and kings, that's what I've done. The whole deck, red cards and kings, okay? So I'm saying everything that's a red card lives in here, and everything that's a king lives in here. You guys good with that? The rest of the cards, the aces through queens that are black, live out here. And notice that 2 of my red cards are in both, because those are my red kings. You guys good with that? Okay. So it says, find the probability of a red card. That's 26 out of 52, or half of the red cards. So a picture of that probability would be this circle, right? Half of the red cards, 26 out of all 52. Find the probability of getting a king. Well, a king would be 4 out of 52. So what's the probability of getting let's go back with a red king or a red, basically we want a red and a king, right? How many reds and kings are there? 2. Okay, so that's 2 out of 52. Okay, and I will tell you, if you had just multiplied these two together, okay, it would have given you this answer because it's and. Have to be careful there with the independence idea, but they're independent, so it would have given you an and. Okay, now question. That's the stuff we just talked about. Red or a king? Well, probability of a red, there was 26 out of 52, right? Plus the probability of a king, 4 out of 52. So we counted everybody in the red circle and everybody in the blue circle, but who did we overcount? Who did we count twice? Oliver. The red kings, right? We double counted the red kings, so you have to subtract the probability of getting a red king minus 2 out of 52. What this formula does up here, it counts all of A, all of B, and then subtracts one of those overlaps so you don't double count. Okay, and so it subtracted out the overlap, and so you would get 28 out of 52, not 30 out of 52, because there would be 28 cards that fit that. Which is what I have written down here for you. Takes out the overlap. Lastly, a new vocab word. What do you do if there is no overlap? It's called mutually exclusive. Okay, so again, you could drive to the bus stop and then ride the bus to school, but normally you either drive to school or you take the bus. So they don't overlap. So it would look something like this, in which case there would be no overlap to subtract. Mutually exclusive, or another word for this is disjoint, when they can't happen at the same time. So now we're going to look at it with a table. Okay, and I hate that all of these are already filled in for you, so just follow along. The table summarizes the grades and genders of a group of math students. Fill in the missing spots, okay? The probability that a student is a female. If it just says is something, your denominator will always be the total. So my total was 56. How many females out of 56? 26 out of 56, but I meant 65. You guys good with that? Okay. The probability that a female and earned an A, you could use the multiplication and addition stuff that I showed you, but you just have to be careful if there's independence, so you'd have to be careful with that for the multiplication. But instead, think about it. How many are female that earned an A? 10 out of 65. The probability that a student did not earn a B. Well, we have 18 A's and 25 C's, that's 43. Or did not earn a B, that's 1 minus the probability of a B, which would be 22 out of 65, which would still give you 43 out of 65. Okay, now we're going to look at the given. The given is the only time your denominator changes. The probability that a student was a male, given that they earned a B. I know this kid earned a B. So I'm not looking at all 65 kids. I'm only looking at these 22 kids that had a B. Given that they had a B becomes the new denominator. How many of them were male? 18 out of 22. Okay. Similarly, what's the probability they earned a B given they were male? Notice these are not the same values. This time, this becomes my denominator, and this becomes my numerator. They don't have, does not mean the same thing. How many of you have seen this before? In secondary 3 or? Okay. All right. So, lastly, what is the probability the student was a male or earned a C? You could use this formula probability of Mel or C is the probability of Mel plus the probability of C minus the probability of Mel and C to take out the overlap. So probability of Mel was 39. And if you think about it, we're taking all of these 39 right here. Okay. All of the people that earned a C. And then what did we double count? We double counted this 13 right here, so we had to subtract it out. Do you have to do it that way? No. Could you have just said this plus this plus this plus this? Yeah. Right? If you want, you can just add up the pieces. All right. So here's some more examples for you to look at, but basically it's just showing you how to do it. You are ready to do number 1 through 8. I think you should just start them, and then I'm here for homework questions, okay? And then we'll move on next time.